The universe is one giant, unsolved mystery, a cosmic puzzle that stretches beyond the edges of our imagination. Every time we think we've uncovered one of its secrets, it throws another enigma our way, leaving even the brightest minds utterly baffled. From the strange behavior of dark matter to the unsettling silence in our search for alien life, space is full of questions that defy easy answers. But what if some of these mysteries aren't just random quirks of the cosmos? What if there are theories, bold, mind-bending ideas that could finally crack the code? Picture this: you're a detective handed a case file filled with the most bizarre, unexplainable phenomena imaginable. Only, instead of a crime scene, your clues are hidden in the swirling depths of black holes, the eerie glow of distant nebulae, and the ghostly whispers of radio waves from the edge of the known universe. This isn't science fiction, it's the real, thrilling challenge astronomers and physicists face every day. And today, we're diving headfirst into 30 of the most astonishing theories that might just explain the unexplainable. Theories so wild, they'll make you question everything you thought you knew about reality itself. Some of these ideas sound like they're ripped straight from the pages of a fantasy novel, parallel universes brushing against our own, hidden dimensions curled up tighter than a coiled spring, even the possibility that our entire existence is nothing more than an elaborate simulation. But here's the thing. Each one of these theories is backed by serious scientific minds, equations scribbled on whiteboards, and observations that refuse to fit into the neat little boxes of conventional wisdom. So whether you're a space enthusiast hungry for the latest cosmic riddles or just someone who loves a good mystery, buckle up. We're about to take a journey through the most tantalizing possibilities that could rewrite the story of the cosmos, one mind-blowing revelation at a time. What if our universe isn't alone? What if it's just one page in an infinite cosmic library, surrounded by countless other universes, each with its own set of physical laws and bizarre possibilities? This is the Multiverse Hypothesis, a mind-bending theory that suggests reality as we know it might be just one fragment of a much grander, weirder existence. And it's not just science fiction. Some of the brightest minds in physics have spent decades wrestling with this idea, trying to answer one of the biggest head-scratchers in cosmology. Why does our universe seem so perfectly fine-tuned for life? Take gravity, for example. If it were even slightly weaker, stars and galaxies would never have formed. If it were stronger, the universe would have collapsed back on itself almost immediately. The odds of all these delicate forces aligning just right seem impossibly slim, unless, of course, there are countless other universes out there where the numbers didn't work out. In those places, life never got a chance to emerge. We just happened to live in the rare universe where everything clicked into place. But how could multiple universes even exist? One leading explanation comes from quantum mechanics, where every possible outcome of an event might spawn its own separate reality. Picture a cosmic kaleidoscope endlessly splitting with every decision, every roll of the dice. Another version, called the bubble universe theory, suggests that new universes constantly bud off from one another like bubbles in a boiling pot. Each one inflates with its own unique physics, some collapsing instantly, others expanding into vast, alien landscapes we can't even imagine, even stranger. Some theories propose that these parallel universes might not be entirely disconnected from ours. Perhaps they brush against our reality in subtle ways, leaving ghostly fingerprints in the cosmic microwave background or creating eerie anomalies that defy explanation. It sounds like something from a Twilight Zone episode, but for scientists grappling with the mysteries of dark energy or the unexpected behavior of distant galaxies, the multiverse idea offers a tantalizing solution. Of course, not everyone's convinced. Critics argue that if we can't observe or interact with these other universes, the theory strays dangerously close to speculation. But here's the thing, science has a funny way of turning the impossible into the undeniable. Not long ago, the idea of black holes or an expanding universe seemed like wild fantasies. Now they're textbook facts. Could the multiverse be next? If so, it wouldn't just solve some of cosmology's biggest puzzles. It would redefine our place in existence itself. What if the answer to one of the universe's greatest mysteries has been hiding in plain sight this whole time, not as some exotic particle, but as countless ancient black holes left over from the birth of the cosmos? That's the bold claim behind the primordial black hole theory, a controversial but increasingly compelling idea that could explain the elusive nature of dark matter. For decades, scientists have known that galaxies behave as if they're far heavier than what we can actually see. Stars orbit their centers at speeds that should fling them into the void, yet something invisible, something we call dark matter, holds them together with its gravitational grip. Most theories assume dark matter is made of undiscovered particles like WIMP or actions, but what if we've been looking in the wrong direction entirely? Primordial black holes offer a tantalizing alternative. These wouldn't be the black holes formed from collapsing stars, but ones that could have sprung into existence in the chaotic first moments after the Big Bang, when denser patches of the infant universe collapsed under their own gravity. Ranging in size from microscopic to mountain mass, they'd be nearly impossible to spot directly, yet their combined gravity could account for the missing mass we've been chasing. The evidence gets even stranger. When astronomers study distant light bending around unseen objects, a phenomenon called gravitational lensing, they occasionally catch flashes of unexplained magnification. Some argue these fleeting distortions could be signatures of primordial black holes drifting silently between us and distant stars. Even more intriguing, the way certain black hole mergers detected by LIGO seem oddly heavy, as if they're relics from an earlier, denser era of the universe. Not everyone's convinced, of course. If primordial black holes were everywhere, why don't we see more lensing events? Why haven't they disrupted star clusters or left clearer fingerprints in the cosmic microwave background? Yet for all the skepticism, the idea refuses to fade. After all, nature often favors the simplest solutions, and what's simpler than an invisible cosmic ingredient we already know exists, just hiding in an unexpected form? If this theory holds, it wouldn't just solve the dark matter puzzle. It would rewrite the story of how our universe grew from a fiery beginning into the structured cosmos we see today. We've all heard of black holes, cosmic vacuum cleaners that swallow everything in their path, even light itself. But what if there's a mirror opposite to these terrifying objects, something that doesn't pull matter in but violently spews it out? Enter white holes, one of the most bizarre and controversial ideas in modern physics. And here's where it gets even stranger. Some scientists believe our entire universe might have burst into existence from one. White holes are essentially black holes running in reverse. Where a black hole's gravity is so intense nothing can escape, a white hole would be a region of space-time where nothing can enter, only eject matter and energy outward at impossible speeds. Think of it like a cosmic geyser erupting with the raw ingredients of reality itself. And according to a radical theory, the Big Bang might have been the ultimate white hole event, a single, universe-creating explosion of space-time. This idea isn't just wild speculation. It emerges from the math of Einstein's general relativity, which allows for white holes as valid solutions to its equations, even if we've never observed one. Some quantum gravity models, like loop quantum gravity, take it further. They suggest that when a black hole reaches the end of its life, it doesn't just vanish but rebounds as a white hole, effectively giving birth to a new universe inside itself. Picture a Russian nesting doll of realities, each born from the remnants of another. The implications are staggering. If true, our universe might not be the first, just one link in an endless chain of cosmic generations. It could also solve one of physics' biggest headaches, the singularity problem. Black holes supposedly crush matter into an infinitely dense point, a concept that makes physicists shudder. But if that singularity flips into a white hole eruption, suddenly the math starts making sense again. Of course, white holes remain purely hypothetical for now. No telescope has ever spotted one, and critics argue they'd violate the second law of thermodynamics, essentially creating energy from nothing. But in a cosmos where dark energy accelerates expansion and particles pop in and out of existence, maybe we shouldn't dismiss the impossible too quickly. After all, if the universe began with the most violent explosion imaginable, who's to say it wasn't a white hole's final act? Hold on to your perception of reality, because what if everything you see, touch, and experience is nothing more than an elaborate cosmic projection? That's the jaw-dropping premise of the holographic universe theory, a mind-stretching idea that suggests our three-dimensional world might actually be encoded on a two-dimensional surface at the very edge of existence. It sounds like something straight out of a sci-fi movie, but this theory has deep roots in some of physics' most perplexing puzzles. The story begins with black holes, those enigmatic cosmic traps where gravity is so intense not even light can escape. Back in the 1970s, physicist Stephen Hawking made a startling discovery. Black holes aren't completely black. They slowly leak radiation, and over eons they evaporate. But this raised a glaring question. If a black hole vanishes, what happens to all the information about the stars, planets, or unlucky astronauts it swallowed? Quantum mechanics insists information can't be destroyed, yet general relativity seems to say otherwise. Enter the holographic principle. In the 1990s, physicist Leonard Susskind and others proposed a radical solution. What if all the information inside a black hole isn't lost but smeared across its event horizon, the point of no return, like a cosmic DVD encoding data in two dimensions? Think of it like a bathroom mirror fogging up. The details of the room aren't gone, they're just translated into a flat, steamy surface. Apply this idea to the entire universe, and suddenly, our 3D reality could be a projection from a vast, distant 2D boundary we can't even see. The implications are staggering. If true, it would mean every tree, every galaxy, even your own thoughts, are really just intricate patterns painted on the fabric of spacetime's edge. This isn't just poetic speculation. The math backs it up. When scientists calculate the entropy of black holes, the numbers mysteriously match what you'd expect if their information was stored on their surfaces, not their volumes. Even more compelling, the principle could bridge the epic feud between relativity and quantum mechanics, two theories that refuse to play nice. Quantum physics thrives on surfaces, while relativity describes the bends and curves of 3D space. The holographic universe might be the translator they've needed. Skeptics, of course, demand proof. If we're living in a hologram, there should be glitches, tiny pixelations in spacetime itself. Some experiments have hunted for these by examining the blurry limits of quantum fields, while others analyze the cosmic microwave background for hidden patterns. So far, no smoking gun, but here's the kicker. Whether the theory holds or not, it's reshaped how we think about space, information, and the very nature of reality. After all, if even black holes, the universe's ultimate information shredders, can't truly erase data, what does that say about the fabric of existence itself? Maybe we're not just in the universe, maybe, in some strange way, we're its reflection. In the vast expanse of the cosmos, few stars have sparked as much intrigue or outright speculation as KIC 8462852, better known as Tabby's star. Named after astronomer Tabitha Boyajian, who first documented its bizarre behavior, this distant sun has left scientists scratching their heads for nearly a decade. Unlike any other star observed, Tabby's star dims unpredictably, sometimes by as much as 20%, a fluctuation so extreme it defies conventional explanation. At first glance, the obvious suspects might be planets or debris passing in front of it. But here's the catch. Even a Jupiter-sized planet would only block about 1% of a star's light. The dips observed around Tabby's star are colossal, irregular, and don't follow any predictable pattern. That's where things get interesting and where some researchers dared to voice a radical idea. Could these mysterious shadows be caused by something built intentionally? The notion of a Dyson sphere, a hypothetical megastructure designed by an advanced civilization to harness a star's energy, suddenly didn't seem so far-fetched. Imagine a vast network of solar collecting panels or a swirling swarm of energy-harvesting satellites encircling the star, blocking its light in strange, asymmetrical ways. It's a concept straight out of science fiction, yet for a brief moment it was on the table as a legitimate possibility. But before we start drafting first contact protocols, let's pump the brakes. Science demands evidence, and the natural explanations are just as fascinating. One leading theory points to colossal clouds of dust, possibly from a recent planetary collision or a swarm of comets caught in chaotic orbits. These wouldn't obscure the star uniformly. Just like Earth's own patchy clouds create uneven sunlight, cosmic dust could explain the erratic dimming. Another idea suggests the star itself might be going through a volatile phase, with immense magnetic storms or internal instabilities causing its light to flicker like a cosmic candle in the wind. Yet, despite years of scrutiny, Tabby's star refuses to give up its secrets. New observations haven't ruled out the megastructure hypothesis entirely, they've just made it less likely. And that's the thrilling part. Whether it's dust, stellar tantrums, or something even weirder, this star reminds us how much we still don't understand. The universe loves a good mystery, and Tabby's star might just be its greatest unsolved enigma for now. What if the very act of looking at the universe changes it not metaphorically, but in a concrete, measurable way? This isn't philosophy or mysticism. It's one of quantum mechanics' most unsettling truths, known as the observer effect. And when you take it to its logical extreme, it leads to a spine-tingling possibility that consciousness itself might be woven into the fabric of reality. Let's start with the double-slit experiment, the crown jewel of quantum weirdness. When scientists fire particles like electrons at a barrier with two slits, they behave in ways that defy common sense. Leave the experiment unobserved, and the electrons act like waves, creating an interference pattern on the screen behind the slits, as if each electron passes through both openings simultaneously. But the moment you set up a detector to see which slit the electron actually takes, the wave pattern collapses. The electrons suddenly behave like tidy little particles, as if embarrassed by being watched. This bizarre phenomenon has fueled wild theories for decades, but one of the most provocative is the idea that consciousness, the act of observation, somehow forces the universe to make up its mind. Some interpretations, like the von Neumann-Wigner hypothesis, take it further, suggesting that reality remains in a fuzzy, undefined state until a conscious observer pins it down. In other words, the cosmos might not exist in a definite way until someone or something perceives it. Enter panpsychism, the ancient philosophy gaining traction in modern physics. If consciousness isn't just a byproduct of brains but a fundamental property of matter, like mass or charge, then everything from atoms to galaxies might have some rudimentary form of awareness. Think of it like this: your smartphone has circuits that process information but no inner experience. Panpsychists argue that at the most basic level, even particles might have a sliver of subjective experience, and complex systems like brains simply amplify it. The implications are dizzying. If true, the universe wouldn't just contain consciousness, it might be conscious, a self-aware cosmos observing itself into existence. This could explain why the laws of physics seem so finely tuned for life, because in some strange loop, life is what brings those laws into being. Of course, critics pounce on the lack of direct evidence. How do you test whether a quark has feelings? Others argue that conflating observation with consciousness is a category error. Quantum observation just means interaction with any measuring device, not a literal mind. But the mystery persists. Why does reality seem to play by different rules when we're not looking? Whether the answer lies in undiscovered physics, the limits of human perception, or something far stranger, one thing's certain: the line between observer and observed might be far thinner than we ever imagined. Ever pause to consider the eerie possibility that none of this, not the stars, not your hands, not even the thoughts in your head, is real? That everything you perceive might be an intricate simulation, lines of code running on some unfathomable computer built by a civilization so advanced we'd seem like ants to them. This isn't the plot of a dystopian film. It's the simulation argument, a serious philosophical proposal with unsettling implications for reality itself. At the heart of this idea is philosopher Nick Bostrom's trilemma, a three-pronged puzzle that forces us to confront a staggering conclusion. Either one, nearly all civilizations at our level of technological development go extinct before achieving simulation capabilities, or two, advanced civilizations lose interest in creating simulations of their ancestors, or three, the kicker: we're almost certainly living in a simulation right now. Why? Because if even one advanced society runs countless ancestor simulations, the odds that we're in the original, real universe become astronomically slim. The Fermi paradox, the deafening silence where alien civilizations should be, might even find an explanation here. If we're in a simulation, the programmers could have simply didn't bother populating the cosmos with other life forms, conserving computational resources. Or worse, Earth is a lonely quarantine zone, a historical reenactment running in isolation. But how would we even test such a wild idea? Some scientists argue that if our universe is a simulation, it might have detectable resolution limits, cosmic pixels, like a video game straining its engine. Physicists have searched for signs in the behavior of high-energy particles, looking for unnatural frame rate glitches in spacetime itself. Others propose that quantum indeterminacy, the way particles exist in multiple states until observed, could be a processing shortcut, the universe optimizing its code to save energy. Then there's the problem of computational brute force. Simulating every atom in a universe like ours would require unimaginable power, unless the simulation only renders what's being observed, like a video game loading graphics as you explore. Sound familiar? It mirrors quantum mechanics' observer effect, where reality seems to solidify only under scrutiny. Of course, skeptics abound. If we're simulations, why do we experience suffering, mosquito bites, or bad coffee? Wouldn't our creators edit out the bugs? And if simulations are so easy to spot, why haven't we found definitive proof? Yet the theory persists, fueled by its uncanny ability to reframe existential questions. After all, if consciousness is just data in a cosmic mainframe, death might be no different than unplugging a server, and free will could be an elaborate illusion in someone else's code. Whether you find the idea terrifying or thrilling, one thing's clear: the simulation argument forces us to question not just the nature of reality, but the very meaning of existence. And if it's true, well, let's hope the programmers left an undo button somewhere. What if the answer to dark energy, the mysterious force stretching our universe apart, has been hiding in plain sight, not as some exotic particle, but as a bizarre new form of matter that defies the laws of physics as we know them? Enter time crystals, structures so strange they sound like science fiction, yet earned their discoverer a Nobel Prize. Unlike ordinary crystals, which repeat their atomic patterns in space, time crystals repeat in time, oscillating indefinitely without any energy input. It's the closest thing we've ever seen to perpetual motion, and it might just hold the key to one of cosmology's greatest puzzles. Picture a clock that never winds down, a dance of atoms locked in an endless rhythm without batteries or outside influence. That's the essence of a time crystal, first theorized in 2012 and created in labs just 5 years later. These structures exist in a perpetual state of low-energy motion, flipping between configurations like an unstoppable metronome. Now, some physicists are asking, could these peculiar objects be lurking throughout the cosmos, their ceaseless jittering driving the accelerated expansion we attribute to dark energy? Here's how it might work. Dark energy is the placeholder name we give to whatever's causing the universe to expand faster and faster, a phenomenon with no known explanation. But if space is peppered with time crystals, their constant oscillations could be generating tiny, repetitive pushes on the fabric of spacetime itself. Alone, one time crystal's effect would be negligible, but scattered across the vastness of the universe like cosmic glitter, their combined influence might add up to the repulsive force we observe. The beauty of this idea lies in its elegance. Dark energy has always been a placeholder, a mathematical fudge factor in Einstein's equations. Time crystals, on the other hand, are real, demonstrable, and already bending our understanding of thermodynamics. Instead of inventing a new particle or field, we'd be repurposing an existing oddity of quantum physics to solve two mysteries at once. Of course, there are hurdles. Lab-created time crystals are microscopic and fragile, surviving only in carefully controlled conditions. Scaling them up to cosmic proportions would require mechanisms we can't yet imagine, perhaps natural processes in the extreme environments near black holes or during the universe's infancy. And critics point out that even if time crystals exist in space, proving they influence expansion would require detecting their subtle fingerprints in the cosmic microwave background or the large-scale structure of galaxies. Yet the possibility tantalizes because it flips conventional wisdom on its head. We're used to thinking of the universe's expansion as something driven by an invisible, intangible force. But what if it's not a force at all? What if it's the emergent property of countless tiny clocks, each ticking away in perfect, endless synchrony? It's a vision as poetic as it is radical, one where the cosmos doesn't just contain time, but is fundamentally built from its rhythms. Imagine a universe where matter doesn't just pull objects together with gravity, it actively pushes them apart with an invisible cosmic repulsion. This isn't some galactic scale magic trick. It's the startling premise behind negative mass, a hypothetical form of exotic matter that could rewrite our understanding of dark energy and the fate of the cosmos itself. At first glance, the concept seems to violate common sense. According to Newton, all objects with mass attract one another. That's why apples fall toward Earth. But negative mass flips this script entirely. Instead of generating attraction, it would produce repulsive gravity, literally pushing normal matter away. Picture two magnets turned inside out. Place a chunk of negative mass near a planet, and rather than falling toward it, the planet would recoil like it had been shoved by an unseen hand. This bizarre behavior might explain one of cosmology's greatest headaches: dark energy. For decades, scientists have struggled to understand why the universe's expansion is accelerating rather than slowing down. Negative mass offers an elegant solution. If vast clouds of this phantom matter are woven into the fabric of space, their repulsive push could be driving galaxies apart at ever-increasing speeds. Unlike dark energy's abstract cosmological constant, negative mass would be a tangible, if utterly alien substance with observable effects on spacetime. The implications get even wilder when you consider how negative mass would warp the structure of reality. In Einstein's general relativity, mass curves spacetime like a bowling ball on a trampoline. Negative mass would create the opposite effect, a sort of anti-dent where spacetime bulges outward. String these distortions together, and you could theoretically construct wormholes, cosmic shortcuts held open by tunnels of repulsive gravity. Some physicists speculate that advanced civilizations might even use negative mass as the ultimate propulsion system, bending space-time to achieve faster-than-light travel without violating relativity. But does this phantom matter actually exist? In 2017, researchers in Washington state made headlines by creating a fluid with negative effective mass in the lab. By cooling rubidium atoms to near absolute zero and manipulating them with lasers, they coaxed the particles into behaving as though they had negative inertia, moving toward a push instead of away from it. Critics were quick to point out that this wasn't true negative mass, just a clever quantum simulation. Still, the experiment proved that certain aspects of this exotic physics aren't purely hypothetical. Skeptics raise valid concerns. Negative mass would require rewriting textbooks on energy conservation, since objects could theoretically accelerate indefinitely without an energy source. There's also the von Neumann catastrophe. If negative and positive masses interact freely, any small imbalance could trigger runaway motion, with chunks of matter accelerating to infinite speeds and tearing the universe apart. Yet for all these hurdles, the idea persists because it solves multiple cosmic puzzles at once. From dark energy to wormholes, negative mass hints at a stranger, more malleable universe than we ever imagined, one where the very fabric of reality might be balanced on a knife's edge between attraction and repulsion. Whether this phantom matter lurks in the cosmos or remains confined to thought experiments, its very possibility stretches the boundaries of physics. After all, if nature allows one type of mass, why not its mirror opposite? The universe has surprised us before, and if negative mass is real, it wouldn't just explain dark energy. It would reveal a cosmos far more dynamic, more unstable, and more astonishing than our textbooks dared to suggest. Picture this: you wake up one day, convinced you've lived a full life, memories, relationships, even the coffee you drank yesterday, only to realize none of it ever existed. You're not a human, not even a biological creature. Instead, you're a lone, disembodied brain, spontaneously assembled by pure chance in the void of space, complete with false memories of a past that never was. This unsettling thought experiment is the Boltzmann brain paradox, a cosmic horror story written not by fiction, but by the cold equations of thermodynamics. The premise begins with Ludwig Boltzmann, a 19th-century physicist who grappled with the nature of entropy. Over unimaginable stretches of time, even in a lifeless, empty universe, random quantum fluctuations could theoretically arrange particles into any configuration, including a fully formed, self-aware brain. In fact, given enough time, these random fluctuations should produce not just one, but countless such minds floating in the darkness, each believing itself to be part of a real, structured world. The implications are dizzying. If the universe tends toward disorder, why do we see such exquisite complexity everywhere? Galaxies, planets, life. One answer is that we're living in a brief, improbable pocket of order, a statistical fluke in an otherwise chaotic cosmos. But here's the twist: according to the math, it's infinitely more likely for a single, isolated brain to pop into existence than an entire ordered universe. So why aren't we all Boltzmann brains, adrift in the void, hallucinating reality? Scientists and philosophers have wrestled with this for decades. Some argue the paradox exposes a fatal flaw in our understanding of cosmology. Others propose that the sheer improbability of Boltzmann brains means our universe must have some deeper structure, a fundamental law or initial condition that prevents such aberrations. String theorists suggest the multiverse could play a role. If countless universes exist, most might be barren, but the rare ones with stable laws like ours naturally host observers who aren't quantum accidents. Then there's the existential whiplash. If Boltzmann brains are possible, how can we trust our own memories? The coffee you remember drinking this morning, the faces of loved ones, even your childhood, these could all be illusions conjured by random particle dances in the abyss. It's a modern take on Descartes' evil demon, but with physics replacing philosophy. Fortunately, most researchers dismiss this as an intellectual funhouse mirror rather than a genuine threat. After all, if we were Boltzmann brains, the universe around us wouldn't obey consistent laws, and science itself would crumble under contradictions. Yet the paradox lingers, a stark reminder that even our most cherished certainties might rest on shakier ground than we'd like to admit. Whether a profound insight or a cautionary tale about pushing theories too far, the Boltzmann brain forces us to confront the fragility of existence. In a cosmos governed by probability and chaos, the line between reality and illusion might be thinner than a single thought. Among the wildest relics theorized to linger from the universe's birth are cosmic strings, spaghetti-thin cracks in spacetime so dense a single inch could outweigh Mount Everest. These aren't your average spaghetti strands, they're defects left over from the Big Bang when the fiery newborn cosmos underwent a phase transition like water freezing into ice. Just as ice forms cracks as it solidifies, spacetime itself might have developed flaws infinitely long, ultra-thin threads of pure gravitational fury. And if they exist, they could be warping the cosmos in ways we're only beginning to untangle. Picture a string thinner than a proton but stretching across the entire observable universe, humming with unimaginable tension. A cosmic string's gravity would be so intense, it wouldn't just bend light, it could slice through galaxies like a knife through smoke. Anything passing near one would experience gravitational lensing on steroids, with twin images of distant stars appearing abruptly on either side, as if reality itself had developed a glitch. Even stranger, these strings wouldn't just sit still. They'd vibrate at near-light speeds, occasionally snapping and sending shockwaves through space-time ripples that might still echo in today's universe as faint gravitational waves. That's where things get cosmic detective-worthy. When astronomers map the distribution of galaxies, they find them clumped into vast filamentary structures like foam bubbles in a bathtub. Ordinary gravity alone struggles to explain these patterns, but cosmic strings could be the missing architects. Their immense gravitational pull in the early universe might have herded matter into those dense threads, seeding the large-scale structure we see today. Even more tantalizing, the faintest whispers of gravitational waves detected by observatories like LIGO could carry the fingerprints of string loops that evaporated eons ago. Not all strings are created equal, though. Some theories propose superconducting cosmic strings which could carry electric currents strong enough to light up galaxies. Others suggest these defects might have birthed entire clusters of black holes in their wake. But here's the twist: despite decades of searching, no one's found definitive proof they exist. The hunt involves scouring the sky for telltale double images of distant quasars, anomalies in the cosmic microwave background, or bursts of radio waves that might betray a string's passage. The stakes couldn't be higher. If cosmic strings are real, they'd be more than just cosmic curiosities. They'd be fossilized imprints of the universe's first terrifying moments. Studying them could reveal what happened a split second after the Big Bang, back when reality was a seething, unstable froth. And if we ever confirmed their existence, it wouldn't just solve mysteries about galaxy formation or gravitational waves. It would prove that spacetime itself is far more fragile and far stranger than we ever dared to dream. Imagine tossing a book into a fire and watching it burn, every word, every sentence reduced to smoke and ash. Now ask yourself, is the information in that book truly lost, or is it somehow preserved in the particles swirling away? That's the essence of the black hole information paradox, a puzzle so baffling it kept Stephen Hawking awake at night. Because when it comes to black holes, the stakes aren't just about books, they're about the fundamental laws of the universe. Hawking's original argument was as elegant as it was unsettling. Black holes, he showed, aren't completely black. They slowly leak radiation, eventually evaporating into nothingness. But here's the catch: that radiation is random, a featureless hiss of energy with no trace of what fell in. If you chuck a spaceship or an entire library into a black hole, all the information about its atoms, its structure, even the thoughts of its crew should vanish forever. That's a problem because quantum mechanics insists information can't be destroyed. It's one of physics' golden rules, the backbone of reality. So who's right, Hawking or quantum theory? The debate ignited a firestorm in theoretical physics, with two main camps emerging. The first, led by Hawking himself for decades, argued that black holes really do obliterate information, forcing us to rewrite quantum mechanics. The other side refused to budge, insisting there had to be a way out, a loophole where information escapes intact. That's where things get wild. One radical solution. Firewalls, picture this. Just beyond a black hole's event horizon, there's not empty space, but a searing wall of high-energy particles. Anything crossing it wouldn't experience the gentle stretching of tidal forces, it'd be vaporized instantly. This firewall would encode the infalling object's information into Hawking radiation, preserving it as the black hole evaporates. But there's a catch. General relativity says crossing the event horizon should feel like nothing special, no fireworks, just smooth sailing toward doom. Firewalls violate that principle, effectively rewriting Einstein's rules. Then there's the holographic principle, which suggests information isn't destroyed but smeared across the black hole's surface, like a cosmic etch-a-sketch. Every particle swallowed imprints a faint pattern on the event horizon, which gets radiated back out over eons. It's a bit like burning that book, but having its words secretly encoded in the smoke swirls. This idea dovetails with string theory and the notion that our three-dimensional universe might be a projection from a two-dimensional boundary, a twist that could reconcile Hawking's findings with quantum law. The implications ripple far beyond black holes. If information can vanish, it undermines quantum determinism, the idea that the past perfectly predicts the future. Lose that, and the universe becomes unknowable at its core. But if information always escapes, even from places as hostile as black holes, it suggests reality is far more resilient than we imagined. Recent breakthroughs hint at progress. Hawking himself eventually conceded that information probably isn't lost, and calculations in string theory seem to confirm it can escape. Yet the how remains hotly contested. Are firewalls real? Is space-time fundamentally holographic? Or is the answer something even stranger, waiting in the equations we've yet to untangle? One thing's certain, solving this paradox wouldn't just close a chapter in physics. It'd reveal the universe's deepest secrets, how it remembers, how it forgets, and what truly happens when reality itself is pushed to the brink. Deep in the direction of the constellations Hydra and Centaurus, something strange is pulling at our galaxy, along with thousands of others with the gravitational might of 1,000,000 billion suns. Astronomers call it the Great Attractor, and despite decades of searching, its true nature remains one of cosmology's most stubborn enigmas. Here's the problem. When we map the motion of galaxies across the cosmos, everything in our local supercluster, including the Milky Way, is being dragged toward this invisible behemoth at over 2 million kilometers per hour. But when we point our telescopes there, we find nothing that should wield such power. So what's really lurking in that cosmic blind spot? The most straightforward explanation is that we're dealing with a colossal supercluster hidden behind the dense star fields of our own galaxy's disk, a region astronomers poetically call the zone of avoidance because dust and stars block our view. Infrared and radio surveys have peeled back some of this cosmic curtain, revealing massive structures like the Norma cluster and the Vela supercluster. Combined, these could account for part of the pull, but the math still doesn't add up. Even with these giants, the gravitational force falls short by a staggering margin. That leaves scientists scrambling for alternatives, some of which veer into the realm of speculative physics. One tantalizing possibility: the Great Attractor might not be a single object at all, but a signpost pointing to something far larger. Beyond Hydra Centaurus lies the Shapley supercluster, the most massive concentration of galaxies in the observable universe. Like a cosmic Matryoshka doll, it's possible we're feeling the gravitational echo of this distant titan. But here's the twist: Shapley alone can't explain the precise trajectories we observe, leading some to wonder if we're missing an even bigger player, perhaps an unfathomably vast structure stretching beyond our current observational limits. Then there's the radical fringe. Could the Great Attractor be evidence of exotic physics, an unevenness in the fabric of spacetime itself? Some modified gravity theories suggest that what we're seeing isn't a hidden mass, but a flaw in Einstein's equations at cosmic scales. Others flirt with the idea of gravitational leakage from extra dimensions, where our universe brushes against a neighboring brane, warping local geometry. It's a stretch, but in a field as perplexing as cosmology, even the wildest ideas get a seat at the table. The truth is, this mystery cuts to the heart of how we understand the universe's structure. If the Great Attractor is just a cluster we haven't fully mapped, it reinforces the standard model of cosmology. But if it defies conventional explanations, we might be staring at the first crack in our understanding of gravity itself. Future telescopes like the Square Kilometre Array could finally pierce the zone of avoidance with unprecedented clarity. Until then, the Great Attractor remains a cosmic tug-of-war between what we see, what we calculate, and what we dare to imagine. Hidden in the vast darkness between stars, there might be entire celestial bodies we've never seen, not because they're too faint or too far, but because they're made of the universe's most elusive particles. Enter neutrino stars, a mind-bending theoretical construct where gravity has corralled trillions upon trillions of neutrinos into dense, dark orbs. Unlike ordinary stars that blaze with light, these would be utterly invisible, their existence betrayed only by the faintest gravitational whispers. Neutrinos are the ghosts of the particle world, tiny, nearly massless entities that barely interact with matter. Trillions pass through your body every second without a trace. Under normal circumstances, they'd never stick around long enough to form anything. But imagine a scenario in the early universe when temperatures and densities were so extreme that neutrinos couldn't just breeze through space, they got trapped, piled up in regions where gravity overpowered their tendency to flee. Over eons, these trapped neutrinos could have collapsed into neutrino stars, objects as massive as suns but with no surface, no light, no electromagnetic footprint whatsoever. Here's where things get compelling. Astronomers have long noticed discrepancies in galactic rotation curves. The way stars orbit the centers of galaxies suggests there's more mass out there than we can see. Dark matter is the usual suspect, but what if some of that missing mass is tied up in neutrino stars? They'd exert gravitational pull just like ordinary matter, yet slip through every observational net. The only hint of their presence might come from rare neutrino interactions in detectors buried deep underground, or the subtle warping of spacetime around them, bending light from background stars in telltale ways. The concept isn't without hurdles. Neutrinos are famously slippery, and getting them to clump together would require conditions far beyond anything in our current universe. Some theories suggest that if neutrinos have even a tiny bit more mass than we've measured, or if exotic physics like sterile neutrinos exist, formation might be possible. Others speculate that these stars could be transient, forming in the universe's fiery infancy, then evaporating as space expanded and cooled, leaving behind only gravitational echoes. What makes the idea so tantalizing is its economy. Instead of inventing entirely new particles to explain dark matter, we might be overlooking structures built from particles we already know. It's like searching for a missing key by ripping apart the couch, only to realize it's been in your pocket all along, just invisible to the naked eye. Whether neutrino stars are real or just a beautiful mathematical fantasy, they remind us that the universe's greatest secrets might not be hidden in the distant cosmos, but woven into the fabric of the ordinary, or in this case, the extraordinarily faint. For nearly a century, the Big Bang has stood as the reigning origin story of our universe, a single, explosive moment birthing everything from a singularity smaller than an atom. But what if that's only half the tale? What if our universe isn't a one-and-done creation, but part of an endless cycle of collapse and rebirth? This is the radical vision of the Big Bounce, a model where universes don't end with a whimper or a crunch, but with a rebound into a new existence. No definitive death, no absolute beginning, just an infinite cosmic heartbeat, expanding and contracting across eternity. The idea isn't entirely new. Ancient Hindu cosmology spoke of universes breathing in and out, while Einstein himself toyed with the notion of a cyclic cosmos before dismissing it. What's revolutionary today is how modern physics, particularly quantum loop cosmology, breathes new life into this ancient intuition. Unlike classical relativity, which breaks down at the singularity of a big crunch, quantum loop theory suggests spacetime isn't infinitely divisible. At the tiniest scales, it's woven from indivisible atoms of space, creating a sort of cosmic fabric that can't be torn. When a collapsing universe reaches this limit, it doesn't vanish into nothingness, it bounces. Imagine squeezing a spring to its limit. The harder you press, the fiercer it pushes back. This changes everything about how we picture cosmic doom. In the old view, a contracting universe would spiral toward infinite density, temperatures soaring beyond comprehension as all matter, energy, and even the laws of physics themselves unravel. But with quantum loops in play, there's a threshold. Gravity becomes repulsive at extreme densities, reversing the collapse into a rebound. The universe isn't erased, it's reset, its energy recycled into a new expansion. It's like hitting the cosmic reboot button, with quantum physics ensuring nothing gets permanently deleted. Even entropy, time's relentless arrow, might get a fresh start. Normally, the universe's disorder increases irreversibly, leading to the gloomy heat-death scenario where all energy disperses into cold uniformity. But in certain bounce models, the extreme conditions of the rebound could iron out entropy, smoothing the cosmic ledger back to zero. Think of it as shaking an etch a sketch until the entire picture clears, ready for a new universe to scribble its story. Critics, of course, raise valid concerns. If each cycle erases the past, how could we ever detect evidence of previous universes? Some theorists propose subtle imprints, patterns in the cosmic microwave background where gravitational waves from a pre-bounce universe might linger, or anomalies in the distribution of galaxies that defy standard Big Bang predictions. Others argue that without observable proof, the Big Bounce remains more philosophy than physics. Yet the theory's elegance is undeniable. It sidesteps the thorny question of what or who lit the fuse of the Big Bang by making beginnings and endings obsolete. No mysterious creator, no multiverse required, just an eternal dance of collapse and renewal, each iteration subtly different from the last. And if true, it paints a breathtaking picture. Our universe isn't a solitary spark in the dark, but one note in an infinite cosmic symphony, playing across time we can't yet measure, in keys we've only begun to imagine. In all the vastness of the cosmos, with its billions of galaxies and trillions of potential habitable worlds, one question looms larger than almost any other: where is everybody? The Fermi paradox, the jarring contradiction between the high probability of alien civilizations and our complete lack of contact with them, has spawned countless theories. But few are as unsettling or as strangely comforting as the zoo hypothesis. What if we haven't heard from extraterrestrials, not because they don't exist, but because they're deliberately keeping their distance? Imagine Earth as a cosmic wildlife sanctuary, carefully observed by advanced civilizations who have chosen to quarantine us not out of hostility, but out of reverence. The idea isn't entirely new. Anthropologists have long debated the ethics of contacting uncontacted tribes, fearing interference could disrupt their cultural evolution. Scale that up to a galactic level, and you've got the zoo hypothesis, Earth as a protected planet, shielded from outside influence until we reach some undefined level of maturity. It's the ultimate cosmic prime directive, an agreement among civilizations to let us grow undisturbed. But how plausible is this scenario? On one hand, it neatly explains the great silence that's puzzled SETI researchers for decades. Despite decades of scanning the skies with radio telescopes, we've heard nothing but static. No signals, no probes, no obvious megastructures. If advanced civilizations wanted to hide, they certainly could, cloaking their presence, masking their transmissions, or observing us through methods we can't yet detect. Some UFO enthusiasts argue that fleeting sightings, the unexplained lights, the erratic movements, could be glimpses of these cosmic zookeepers checking in, though mainstream science remains skeptical of such claims. Yet the zoo hypothesis raises as many questions as it answers. Why would every single civilization in the galaxy agree to such a non-interference pact? On Earth, human history shows that whenever one culture discovers another, contact, peaceful or otherwise, is almost inevitable. And what exactly is the threshold for maturity, technological advancement, ethical development, the ability to travel between stars? If we're being monitored, who decides when we're ready to join the galactic community? Even more unsettling is the possibility that we're not just in a zoo, we're in a lab. Some variations of the hypothesis suggest Earth could be an experiment, a controlled environment where some unknown variable is being studied. Perhaps civilizations arise frequently, but most self-destruct, and we're being observed to see if we'll beat the odds. Or maybe we're a rarity, a data point in a grand cosmic census on the evolution of intelligence. Critics counter that the zoo hypothesis is little more than an elaborate just-so story, a way to explain away our loneliness without evidence. After all, if aliens wanted to avoid us, why leave even ambiguous traces like UFO sightings? And why wouldn't at least one rebellious civilization break the rules and make contact? Others argue that the sheer age of the universe makes the idea untenable. If civilizations have existed for millions of years longer than us, wouldn't their idea of non-interference be so advanced we wouldn't even recognize it as observation? The debate ultimately circles back to the core mystery of the Fermi paradox, whether the answer lies in the zoo hypothesis, self-destructive tendencies of civilizations, or something even stranger. The silence of the cosmos remains one of science's greatest puzzles. But if the hypothesis is correct, there's a peculiar irony to it. Humanity's relentless search for extraterrestrial life might one day be rewarded not by a message from the stars, but by the realization that we were being watched all along quietly, patiently, from the shadows of the cosmic exhibit hall. What if the deepest secrets of the universe aren't written in equations we know, but in a bizarre, 8-dimensional number system so strange, even mathematicians call it the crazy uncle in the attic? Meet the octonians, a numerical realm where the familiar rules of arithmetic break down, where multiplying numbers in different orders gives different results, and where physicists are finding eerie clues that this mathematical oddity might be the hidden code stitching reality together. At first glance, octonians sound like abstract nonsense. While we're used to numbers on a line, one dimension, complex numbers with an imaginary component, 2 dimensions, or even quaternions that help program 3D graphics, 4 dimensions, octonians explode into 8 dimensions. They're so counterintuitive that their discoverer, mathematician John Graves, initially doubted his own work. Yet here's the twist: when physicists plug octonians into their models, they align uncannily well with the behavior of fundamental particles, almost as if the universe itself runs on this exotic math. String theory, the leading framework for unifying quantum mechanics and gravity, already suggests our cosmos has more dimensions than we perceive, tiny, curled-up spaces hidden at every point. Octonians might hold the key to why. The unique symmetries of octonian algebra mirror the strange patterns seen in particle physics, particularly the standard model's 3 generations of matter like electrons, muons, and tau particles. It's as if nature chose this 8-dimensional math as its programming language, and we're only now deciphering the syntax. One electrifying example. The strong nuclear force which glues quarks together inside protons and neutrons behaves in ways that conventional math struggles to describe, but octonions provide a natural framework for its quirks. Similarly, the unexpected connection between gravity and electromagnetism in certain unified theories snaps into focus when octonions enter the picture. Some researchers even speculate that the infamous unreasonable effectiveness of mathematics in physics, or why abstract equations so perfectly model reality, stems from octonions being the universe's native tongue, with our familiar math just a clumsy translation. Critics counter that octonions are too weird to be physically real. Their non-associative nature, where a times b times c doesn't equal a times b times c, makes them notoriously hard to work with. Yet this very strangeness might explain quantum entanglement's spooky action at a distance, where particles instantly influence each other across vast spans. If spacetime is built from octonionic geometry, entanglement could be a feature, not a bug, a direct result of quantum threads woven through higher dimensions. Whether octonions are the ultimate theory of everything or just a fascinating red herring, their emergence in physics marks a thrilling frontier. After centuries of assuming the universe counts in 4s or 10s, we might need to embrace the madness of 8s. And if that's true, the cosmos isn't just stranger than we imagined. It's stranger than we can imagine, running on math that defies logic to create the order we see. The cosmos has a secret it's desperate to keep, an enigma so baffling. It hints at forces beyond the edges of everything we know. Astronomers call it the dark flow, and it's exactly as eerie as it sounds. Picture this: galaxy clusters, each containing thousands of galaxies, aren't just drifting randomly through space. Instead, they're streaming toward a single, unseen point in the distant void like iron filings drawn to a hidden magnet. The strangest part, this mysterious attractor lies beyond the observable universe, tugging at matter with gravitational fingers we can't see. First detected in 2008 by studying the subtle distortions in the cosmic microwave background, the afterglow of the Big Bang, the dark flow defies everything we understand about cosmic motion. According to standard cosmology, the universe's expansion should scatter galaxies evenly in all directions, like raisins in rising bread dough. Yet hundreds of clusters are hurtling toward a specific patch of sky near the constellations Centaurus and Vela at speeds exceeding 2 million miles per hour. That's not just unusual, it's outright impossible under current models unless something outside our universe is pulling them. So what could it be? One spine-tingling possibility is that we're feeling the gravitational influence of a parallel universe. Just as the moon's gravity tugs Earth's oceans to create tides, a neighboring cosmos brushing against ours might be warping spacetime on a colossal scale. This isn't pure fantasy. The multiverse theory suggests other universes could exist mere millimeters away in higher dimensions, separated by membranes we can't perceive. If one of those universes had a region of extreme mass, a supercluster of galaxies, say, its gravity might leak through, sculpting the dark flow like an invisible hand. But there's a catchier explanation closer to home: relics from the Big Bang itself. During cosmic inflation, the universe's explosive growth spurt in its first fraction of a second, space stretched faster than light, leaving some regions forever beyond our observational horizon. If inflation wasn't perfectly uniform, it could have created vast density imbalances, pockets of hyper-compressed spacetime that now lure matter like cosmic sirens. Alternatively, the dark flow might trace the scars of a long-ago collision between our infant universe and another bubble of reality, a crash so violent it left permanent ripples in gravity's fabric. Skeptics argue the dark flow could be an illusion, a statistical fluke, or a quirk in how we interpret the cosmic microwave background. Yet as measurements improve, the signal persists, whispering of forces we've yet to name. If confirmed, it wouldn't just rewrite cosmology textbooks, it would shatter the very definition of the universe. After all, how can we call something the universe if something beyond it is reaching in, pulling strings we can't even see? Whether it's evidence of the multiverse, cosmic scars, or something even stranger, the dark flow forces us to confront an unnerving truth: we might not be the only show in town. And whatever's out there, it's got gravity on its side. Quantum Darwinism flips everything we thought we knew about reality on its head. Because what if the solid, predictable world around us isn't fundamental at all, but an illusion forged by survival of the fittest information? At the quantum level, particles exist in bizarre superposition states where they're spinning both clockwise and counterclockwise, here and there, dead and alive, yes, like Schrödinger's unfortunate cat. Yet when we look, we always see one definite outcome, never the blur of possibilities. The question that's haunted physicists for decades is simple. Why does quantum weirdness vanish the moment we observe it, and who or what decides which version of reality we get? That's where quantum Darwinism strides in with a radical answer. Classical reality emerges because the environment itself acts as a ruthless editor, favoring certain quantum states and discarding others. Picture a quantum system, an electron, a photon, or yes, even that poor hypothetical cat interacting with its surroundings. Every collision with an air molecule, every stray photon bouncing off it, leaves a tiny imprint, like countless witnesses scribbling notes about what they observed. Over time, only the most stable, redundant imprints survive, the ones multiple observers agree on. The rest fade into oblivion, drowned out by the consensus. It's survival of the fittest, but for information, hence the name. This elegantly solves Schrödinger's paradox. The cat isn't both dead and alive in our experience because the environment has already voted on its fate. The air molecules in the box, the radiation detector, even the atoms in your eyeballs all register a single outcome, amplifying it until the alternative becomes statistically irrelevant. No mystical collapse of the wave function, no need for conscious observers to magically bend reality, just a natural process where robust information thrives and fragile possibilities wither. The implications ripple far beyond cats in boxes. Quantum Darwinism suggests that the reason we all agree on the position of the moon or the color of the sky isn't because those things are fundamentally real, but because their quantum states have been redundantly copied into the environment trillions of times. It's a cosmic game of telephone where only the clearest signals make it through. Even time's arrow might emerge from this process. The past seems fixed because its quantum states have been thoroughly recorded by the universe, while the future remains fuzzy, its possibilities still up for grabs. Critics argue this merely kicks the can down the road. Who or what determines which interactions count as observers? Others point out that certain quantum experiments, like delayed choice tests, still defy intuitive explanation. But if quantum Darwinism holds, it'd mean reality as we know it isn't the bedrock of existence, just the loudest echo in a quantum hall of mirrors. A story the universe tells itself again and again until we mistake it for the truth. And that's a twist even Schrödinger might not have seen coming. Imagine the universe as a frozen lake on a bitterly cold winter morning. The ice seems solid, unbreakable until, without warning, a single crack races outward, shattering the surface in an instant. Now picture that same scenario playing out not on a lake, but across the fabric of spacetime itself. This is the chilling premise behind vacuum decay, a theoretical doomsday scenario where the very ground rules of reality could rewrite themselves at the speed of light, and we'd never see it coming. At the heart of this cosmic horror story lies the Higgs field, an invisible energy ocean that permeates every corner of the universe. It's this field that gives particles their mass, acting like cosmic molasses that slows them down what we experience as weight. For decades, physicists assumed this field sat in its lowest possible energy state, what they call the true vacuum. But unsettling calculations now suggest we might be living in a false vacuum, a precarious high-energy state that could, at any moment, drop into a more stable configuration. Here's where the nightmare begins. If a tiny patch of the universe transitioned to this true vacuum, perhaps through a random quantum fluctuation, it would create an expanding bubble where the laws of physics as we know them cease to exist. Inside this bubble, the Higgs field would take on a new value, altering the mass of every particle instantaneously. Electrons might become too heavy to form atoms. Quarks could lose the ability to bind into protons and neutrons. Even the fundamental forces gravity, electromagnetism, could unravel into something unrecognizable. Worse yet, this bubble would expand at light speed, erasing the old universe faster than any signal could warn of its approach. The math behind this scenario is as precise as it is terrifying. Measurements of the Higgs boson's mass at the Large Hadron Collider suggest our vacuum might indeed be metastable, stable enough to last billions of years, but not necessarily forever. Some estimates put the probability of a decay event occurring within our observable universe at startlingly high odds, perhaps as likely as 1 in 10 billion per year. That sounds reassuring until you realize the universe has existed for nearly 14 billion years already. It's like playing Russian roulette with a cosmic-scale revolver, where each passing moment spins the cylinder anew. Critics argue that vacuum decay might be impossible, that unknown physics could stabilize the Higgs field, or that the universe's accelerating expansion might prevent bubbles from ever merging. Others point out that if the process were truly likely, it should have happened somewhere in our past light cone, meaning we wouldn't exist to ponder it. But the most unsettling possibility isn't that vacuum decay will happen, it's that it already has. Somewhere beyond our cosmic horizon, an invisible wave of annihilation could be racing toward us right now, rewriting physics one light year at a time. What makes this scenario uniquely disturbing isn't just the utter annihilation it promises, but the total absence of drama. No explosions, no black holes, no warning. One moment, reality as we know it exists; the next, it's been overwritten by new rules that may not even allow for life. It's the ultimate cosmic quietus, a silent reboot where the universe forgets its own past. Yet there's a strange comfort in knowing that if it happens, we'll never feel a thing. The universe might die with a whimper, but until then, every second it persists is a defiance of the odds, a fragile miracle of stability in an uncertain cosmic sea. Deep in the cosmic shadows, our sun might not be the solitary ruler of its domain after all. What if it shares its throne with a dark, distant twin, a failed star, or a massive planet silently lurking at the fringes of our solar system, stirring chaos every few million years? This is the Nemesis star hypothesis, a theory as dramatic as it is divisive, and it just might explain one of Earth's darkest mysteries, the eerie regularity of mass extinctions. For decades, paleontologists have noticed a grim pattern in the fossil record. Every 26 million years or so, life on Earth suffers a catastrophic die-off. The dinosaurs are the most famous victims, but they're far from alone. These extinction events line up with alarming precision, like clockwork written in bone and ash. The question is, what cosmic clock could possibly keep such terrible time? Enter Nemesis, the hypothetical Death Star companion to our Sun. The idea is chillingly simple. If our Sun has a dim binary partner, a brown dwarf or a rogue gas giant, its elongated orbit could periodically jostle the Oort cloud, that vast shell of icy debris at the solar system's edge. Each time Nemesis swings close, its gravity would send a hail of comets screaming toward the inner planets, turning Earth into a shooting gallery. It's a celestial sniper theory, one silent predator, triggering global devastation from the shadows. Recent infrared surveys have reignited the debate. While no smoking gun has been found, telescopes like WISE, the Wide Field Infrared Survey Explorer, have spotted faint, cold objects drifting in the interstellar dark brown dwarfs so dim they're nearly invisible. Some argue Nemesis could be hiding among them, camouflaged by distance and dust. Others point to tantalizing gravitational anomalies in the outer solar system, subtle tugs on distant objects like Sedna that suggest something massive is out there. But here's the twist: Planet 9, the hypothetical giant thought to orbit beyond Neptune, might actually be muddying the waters. Discoveries of oddly clustered Kuiper belt objects initially fueled speculation about a hidden planet, but their orbits don't quite match Nemesis's predicted timeline. Could Planet 9 be a red herring, a distraction from the real villain lurking even farther out? Or is Nemesis itself the misdirection, a ghost story we've spun to explain patterns that have simpler, if less cinematic, causes? The stakes couldn't be higher. If Nemesis exists, its next perihelion could already be sending a wave of doom our way, a silent executioner moving at cosmic speeds. Yet the lack of direct evidence leaves room for doubt. Maybe the extinctions are just statistical noise or the result of Earth's own tectonic tantrums. But until we scour every corner of the sky, Nemesis remains a specter in the data, a shadow that refuses to fade. After all, the universe loves its monsters, and what's scarier than a killer we can't even see? For years, the Pioneer 10 and 11 spacecraft baffled scientists with a mystery as persistent as it was perplexing, an unexplained deceleration, as if some invisible hand was gently tugging them backward into the solar system. Launched in the early 1970s, these trailblazing probes should have coasted through the void with near-perfect predictability, their trajectories governed by the reliable laws of gravity. Yet by the 1980s, researchers noticed something was off. Both Pioneers were slowing down ever so slightly, as though moving through an unseen cosmic molasses. The discrepancy was tiny, just a fraction of a nanometer per second squared, but over decades and billions of miles, it added up to a glaring anomaly that defied explanation. At first, theories ranged from the tantalizing to the outlandish. Could it be the gravitational pull of undiscovered dark matter, a flaw in Einstein's general relativity? Some even dared to whisper about unknown physics, a fifth force acting at solar system scales. The Pioneer anomaly became a rallying cry for those convinced our understanding of gravity was incomplete, a puzzle as frustrating as it was irresistible. Then, in 2012, after years of painstaking analysis, a team of researchers cracked the case, and the answer was hilariously mundane. The culprit wasn't dark matter or new physics, but something far more ordinary: heat. Here's the twist: the Pioneers weren't just gliding through space, they were glowing with it. Their radioisotope thermoelectric generators, the nuclear batteries powering their instruments, emitted heat that radiated unevenly from their asymmetrical bodies. This thermal radiation acted like a tiny but constant push, a photon recoil effect that nudged the probes backward. Once scientists meticulously modeled this thermal pressure, accounting for every watt of energy bouncing off antennae and instrument panels, the anomaly vanished. The universe, it seemed, hadn't been breaking its own rules after all. Yet the story doesn't end there. While the Pioneer mystery was solved, other spacecraft continued to dance to unexplained rhythms. The Galileo and Ulysses probes exhibited similar tiny deviations, while New Horizons, the plucky explorer that gave us the first close-up of Pluto, has shown its own minuscule but stubborn discrepancy. Some researchers argue these could just be unaccounted for thermal effects, but others wonder if there's a deeper pattern at play. Could there still be gaps in our understanding of how heat radiates in the vacuum of space? Or is there something else, a subtle, systemic error in how we track deep space trajectories? The lingering uncertainties serve as a humbling reminder. Even in an age of precision cosmology and gravitational wave detectors, the solar system still holds surprises. The Pioneer anomaly's resolution was a triumph of scientific rigor, but it also underscores how easily we can mistake the ordinary for the extraordinary, and how often the universe's most tantalizing mysteries turn out to be hiding in plain sight, waiting for us to look at them from the right angle. On a quiet August night in 1977, a radio telescope in Ohio picked up something extraordinary, a 72-second burst of radio waves so intense, so anomalous that the astronomer who discovered it scrawled, "Wow," in red ink across the data printout. Decades later, that exclamation still defines one of the most tantalizing mysteries in the search for extraterrestrial intelligence. The signal came from the direction of the constellation Sagittarius, blazing at a frequency near 1420 MHz, precisely the range scientists predicted an alien civilization might use to broadcast its existence. It was the perfect candidate for a cosmic hello, and then it vanished, never to repeat. Modern algorithms have dissected the WOW signal down to its quantum bones, yet its origins remain fiercely debated. One leading theory suggests it wasn't aliens at all, but something far more mundane, a comet. In 2017, researchers proposed that two passing comets, shrouded in hydrogen clouds, could have reflected radio emissions from Earth back to us, creating the illusion of a distant transmission. But here's the problem. Those comets weren't actually in the telescope's field of view when the signal arrived. Worse, the WOW signal's frequency was locked to a narrow band, drifting like a whisper on the cosmic wind behavior comets don't typically exhibit. If it was a reflection, it defies everything we know about how such echoes should behave. The signal's sheer intensity is another puzzle. Natural cosmic radio sources, pulsars, quasars, even the afterglow of the Big Bang tend to smear across a range of frequencies. The WOW signal, by contrast, was surgically precise, vanishing abruptly outside its tiny band. That's the kind of signature you'd expect from a targeted transmission, not a celestial accident. And then there's the silence. Despite countless follow-up scans of the same patch of sky, not a single blip has ever matched it. If this was a comet's doing, why haven't we seen a repeat performance from other icy wanderers? Skeptics counter that absence of evidence isn't evidence of aliens. The universe is vast, and rare, one-off events are statistically inevitable. But the WOW signal's defenders fire back with a haunting question. If it was just noise, why does it tick every box on our hypothetical alien broadcast checklist? From its frequency to its duration to its isolation, it's as if the cosmos handed us a riddle wrapped in static, one we're still scrambling to decode. Perhaps the truth lies somewhere between the extremes. Maybe the signal was a freak alignment of natural phenomena we don't yet understand, a cosmic coincidence so perfect it mimics intelligence. Or maybe, just maybe, it was exactly what it seemed, a fleeting shout across the void, a moment of contact lost in time. Until another WOW echoes from the stars, we're left with a mystery that refuses to fade, a whisper from the dark that still dares us to believe. In October 2017, astronomers spotted something unprecedented hurtling through our solar system, a bizarre, cigar-shaped object moving so fast it could only have come from another star. Named Oumuamua Hawaiian for Scout, it became the first confirmed interstellar visitor ever detected. But what made Oumuamua truly extraordinary wasn't just its origin. It was how it behaved. As it raced away from the sun, something inexplicable happened. Instead of slowing down as expected, Oumuamua accelerated, as if pushed by an unseen force. Mainstream astronomers chalked it up to outgassing, the same process that makes comets sprout tails as sunlight vaporizes their icy surfaces. The catch: Oumuamua showed no visible coma or tail, no telltale puff of dust or gas. This left scientists scrambling. If it wasn't outgassing, what provided the thrust? Enter Harvard astrophysicist Avi Loeb with a jaw-dropping hypothesis. Oumuamua wasn't a naturally occurring space rock at all. It might have been an alien solar sail, a lightweight, wafer-thin structure designed to catch the momentum of starlight, much like a boat's sail harnesses the wind. Loeb pointed to Oumuamua's bizarre shape 10 times longer than it was wide, and its unusual brightness variations as potential evidence of artificial construction. A solar sail, he argued, would explain the acceleration without requiring outgassing, while the object's tumbling motion could suggest damage or intentional deployment. The backlash was immediate. Critics countered that Oumuamua's acceleration could be explained by evaporating nitrogen ice, a substance that wouldn't leave the same dusty trail as water ice. A nitrogen iceberg, they proposed, might have shed invisible gas as it warmed, nudging the object forward without the usual comet-like display. Others suggested exotic hydrogen ice or even a fractal-like dust aggregate formed in the cold outer reaches of a distant star system. Each theory had its flaws, but all aimed to anchor Oumuamua in known physics rather than invoking extraterrestrial technology. Yet Loeb's hypothesis refuses to fade. Solar sails, though futuristic, are far from science fiction. Humanity has already tested light-powered spacecraft like Japan's Ikaros, and Oumuamua's peculiarities stack up. Its reflectivity was unusually high, its shape unnaturally elongated, and its tumbling pattern unlike any natural asteroid. Most damning for the nitrogen theory, no known process in nature creates large, pure nitrogen icebergs. They'd either fracture under their own stress or sublimate long before reaching interstellar space. The debate crystallizes a fundamental tension in science. When do we entertain extraordinary explanations, and when do we cling to the familiar? Oumuamua's true nature may remain forever uncertain. It's now beyond the reach of our telescopes, streaking toward the outer solar system. But its legacy endures as a cosmic Rorschach test. For some, it's a lesson in the universe's capacity for odd but natural phenomena. For others, it's a tantalizing whisper that we might not be the only architects in the galaxy. Either way, Oumuamua reminds us that the universe is still full of surprises and that some mysteries refuse to be neatly solved. Black holes aren't just cosmic vacuum cleaners. They might be the universe's ultimate quantum teleportation devices. Imagine two black holes born from the same stellar collision, separated by billions of light years, yet forever bound by an invisible thread. Now picture that thread not as a metaphorical connection, but as a literal tunnel through space-time, a wormhole stitched together by the strange magic of quantum entanglement. This is the AR equals EPR conjecture, a theory so audacious it ties together Einstein's greatest hits with quantum weirdness to rewrite how we think about the fabric of reality. The story starts with two of Einstein's brainchildren. In 1935, he and Nathan Rosen published a paper showing that black holes could theoretically connect via bridges in spacetime, Einstein-Rosen bridges, or what we now call wormholes. That same year, Einstein teamed up with Boris Podolsky and Rosen again to describe quantum entanglement, the spooky phenomenon where particles instantly influence each other across vast distances, which Einstein famously dismissed as spooky action at a distance. For decades, these ideas lived in separate realms: wormholes as speculative relativity math, entanglement as a quantum quirk. Then, in 2013, physicists Juan Maldaisner and Leonard Susskind dropped a bombshell. What if they weren't separate phenomena at all? What if entanglement was the wormhole? Here's where the universe gets a serious upgrade. Under equals EPR, when two black holes become entangled, their interiors aren't just linked by abstract quantum correlation, they're physically connected by a microscopic wormhole. It's as if the universe, faced with the problem of keeping entangled particles in sync, warped space-time itself to create a shortcut. This flips traditional physics on its head. Instead of entanglement being some intangible quantum handshake, it becomes a geometric feature of space-time woven into the cosmos's very structure. The implications for teleportation are staggering. If ER equals EPR holds, you could theoretically toss a qubit, a quantum bit of information, into one black hole and watch it emerge from its entangled partner, traversing the wormhole faster than light. This isn't sci-fi transporters beaming Kirk to alien planets, but something even wilder. Information skipping across the universe via spacetime's hidden backdoors. Labs have already demonstrated quantum teleportation on Earth, transmitting data between entangled particles across miles. Scale that up with black holes as cosmic routers, and suddenly the universe looks like a vast, interconnected network where distance is an illusion. But there's a catch, or several. First, the wormholes in this scenario are microscopic. Trying to send anything larger than a subatomic particle would snap the tunnel like a rubber band stretched too far. Second, these wormholes are inherently unstable. Without some exotic negative energy propping them open, they'd collapse before anything useful could traverse them. And third, even if you could stabilize one, there's no guarantee you'd exit in one piece. The tidal forces near a black hole singularity would spaghettify you faster than you could say quantum paradox. Critics argue ER equals EPR is more mathematical poetry than testable physics, a beautiful analogy without experimental teeth. Yet recent advances in quantum gravity simulations suggest otherwise. In 2020, Google's Sycamore quantum processor simulated a holographic wormhole by entangling qubits, a small-scale proof of concept that the math might hold water. And if future telescopes detect unexpected correlations between distant black holes like synchronized X-ray pulses with no classical explanation, it could hint at entanglement's hidden architecture shaping spacetime itself. What makes ER equals EPR so revolutionary isn't just the promise of cosmic shortcuts, but the way it blurs the line between quantum mechanics and gravity. For a century, these two pillars of physics have refused to reconcile. But if entanglement builds wormholes and wormholes encode entanglement, then spacetime itself might be a quantum error-correcting code, a holographic projection of deeper, more fundamental connections. It's a vision of reality where separation is an illusion, where every particle, every star, every black hole is secretly holding hands across the void, bound by threads we're only beginning to see. And if that's true, the universe isn't just stranger than we imagined. It's stranger than we can imagine, a cosmic tapestry woven from quantum stitches we've yet to fully unravel. The cosmic microwave background, the oldest light in the universe, should be a perfectly random snapshot of the primordial cosmos, a frozen echo of the Big Bang's aftermath. But when scientists mapped its subtle temperature fluctuations, they stumbled upon something that sent chills down the spines of cosmologists, an eerie alignment that defies everything we know about cosmic isotropy. Dubbed the axis of evil, this mysterious pattern shows large-scale fluctuations in the CMB weirdly oriented along the same plane as our solar system, as if the universe itself were whispering that we occupy a disturbingly special place. At first glance, the name sounds like hyperbole, but the implications are profound. According to standard cosmology, the universe should look the same in all directions, with no preferred axis or center. Yet multiple independent analyzers, from NASA WMAP to the Planck satellite, keep revealing this same unsettling signal. The CMB's hot and cold spots aren't scattered randomly. They appear to pivot around an invisible axis that just happens to line up with Earth's ecliptic plane. The odds of this happening by chance, less than 1 in 1,000. Either we're seeing a statistical fluke of universe-shattering improbability, or something fundamental in our understanding of reality is missing. One spine-tingling possibility is that the axis of evil is a fossil, a scar left behind by a pre-Big Bang structure. Some theories, like conformal cyclic cosmology, suggest our universe is just one in an endless cycle of expansions and contractions. If true, the CMB anomalies could be imprints of a previous cosmic era, like shadows cast by long-dead universes onto ours. Alternatively, the axis might hint at exotic physics, a primordial magnetic field, a space-time defect, or even the gravitational tug of a parallel universe brushing against ours in higher dimensions. Then there's the unsettling alternative. We're seeing the ghost of our own limitations. Could the alignment be an artifact of measurement bias? The solar system moves through the CMB at about 370 kilometers per second, a motion that should create a subtle dipole pattern in the data. But correcting for this kinematic dipole doesn't erase the axis of evil. Others argue that galactic dust or foreground interference might skew the results, yet meticulous filtering leaves the signal stubbornly intact. The deeper we look, the more it resists dismissal. Skeptics counter that humans are pattern-seeking creatures, prone to imagining significance in noise. They point to the "look elsewhere" effect, the statistical inevitability that somewhere in the vast CMB data, something will appear anomalous. But the axis of evil isn't some minor blip. It's a large-scale asymmetry that challenges the cosmological principle itself, the bedrock assumption that the universe is homogeneous at grand scales. If it's real, it forces us to confront a universe that might not just be stranger than we imagined, but stranger than our theories even allow. Whether it's a clue to deeper physics or a cosmic mirage, the axis of evil lingers like an unsolved equation at the blackboard of cosmology. It taunts us with questions. Are we truly insignificant observers in a vast, indifferent cosmos? Or is the universe somehow aware of us, its structure subtly tilted toward the one place we call home? Until we crack this enigma, the CMB remains not just a map of the universe's birth, but a riddle written in the faintest glow of creation itself. Imagine an entire galaxy functioning like a vast, self-regulating organism. Not just a random scattering of stars and planets, but a coordinated system fine-tuned to nurture and sustain life. This is the audacious leap of the Galactic Gaia hypothesis, taking Earth's biosphere concept and expanding it to cosmic proportions. Named after the ancient Greek goddess of Earth, the original Gaia theory suggests our planet isn't just a rock hosting life. It's a complex, self-adjusting system where biology and geology interact to maintain conditions suitable for survival. Now, some researchers dare to ask, could galaxies operate the same way? At first glance, the idea seems preposterous. Galaxies are unimaginably vast, their stars separated by light years of near-perfect vacuum. But consider the eerie precision of our own Milky Way structure. The galactic habitable zone, a narrow annulus where conditions are just right for life, isn't just a happy accident. It's shaped by forces that seem almost orchestrated, not too close to the chaotic, radiation-blasted center, not so far out that heavy elements needed for planets are scarce. Supernova seed space with life-building materials while avoiding sterilizing nearby systems. Even the galaxy's spiral arms, which could fling planets into deadly orbits, appear timed to minimize disruption to life-bearing worlds. The more we study it, the more the Milky Way feels less like a random stellar junkyard and more like a carefully tuned ecosystem. This is where pulsars, cosmic lighthouses left behind by dead stars, come into play. These ultra-precise timekeepers emit radio pulses with clockwork regularity, making them nature's most reliable metronomes. Intriguingly, some pulsars show subtle irregularities in their ticking, tiny deviations that could be mere glitches or something far stranger. If a galaxy were indeed engineering itself to optimize for life, one way to detect it might be through anomalies in pulsar timing. Imagine a scenario where advanced civilizations, acting as galactic-scale stewards, subtly manipulate stellar orbits or energy flows to stabilize habitable zones. Their interventions, though imperceptible to us directly, might leave faint fingerprints in the rhythm of pulsars like a conductor adjusting an orchestra's tempo. Critics argue this veers dangerously close to teleology, the discredited idea that nature has purpose. Yet proponents counter that self-organization isn't mystical. It's a well-documented phenomenon from ant colonies to neural networks. If simple systems can exhibit emergent intelligence, why not galaxies? After all, Earth's biosphere maintains stable temperatures despite the sun growing hotter over billions of years. On a galactic scale, perhaps supermassive black holes act as regulatory hearts, with stellar orbits and gas flows serving as cosmic feedback loops. The real controversy isn't whether galaxies can self-regulate, but whether this regulation could ever become deliberate, a transition from homeostasis to something resembling intention. The implications are staggering. If true, the Galactic Gaia hypothesis wouldn't just redefine our place in the universe. It would suggest life isn't an accident, but an integral part of cosmic architecture. Pulsar timing arrays, like the upcoming Square Kilometre Array, could soon provide the data to test this. Should they uncover patterns inconsistent with natural processes, we might be forced to confront a universe where galaxies don't just harbor life, they cultivate it. And that changes everything. What if the past you think you know is nothing more than an elaborate illusion, a grand historical hoax spanning centuries? This is the startling claim of the phantom time hypothesis, a fringe theory suggesting that 300 years of history, roughly between the years 600 and 900, never actually happened. Instead, proponents argue this period was entirely fabricated by powerful medieval rulers and the Church, stitching together a false chronology to legitimize their authority. At first glance, it sounds like pure conspiracy fodder, but delve deeper, and you'll find a strange web of anomalies that keep this radical idea stubbornly alive. The theory hinges on peculiar gaps in the archaeological record. Buildings and artifacts from this supposed 300-year span often appear suspiciously scarce or stylistically inconsistent. Take the Aachen Cathedral in Germany, a UNESCO World Heritage Site. Its construction is traditionally dated to the reign of Charlemagne in the 8th century, yet some architectural features seem eerily similar to structures from much later periods. Could this be evidence of a timeline squeezed together like an accordion? Even more puzzling are tree ring data from ancient wood samples, which occasionally show discrepancies when matched against historical timelines. Phantom time theorists pounce on these inconsistencies, arguing they betray a manufactured history. Radiocarbon dating, the gold standard for verifying ancient materials, isn't immune to criticism either. The method relies on measuring the decay of carbon-14 isotopes, but its accuracy depends on precise calibration curves, many of which are derived from historical records the phantom time hypothesis calls into question. If those records are flawed, the entire calibration could be skewed, creating a feedback loop where dating methods confirm a timeline that never existed. It's a classic case of circular reasoning, and while mainstream scholars dismiss these concerns as fringe, the debate exposes just how much we rely on interconnected assumptions to reconstruct the past. Yet the theory unravels under scrutiny. Byzantine, Islamic, and Chinese chronicles from the phantom centuries independently document events that align neatly with Western timelines. The idea that multiple civilizations across continents could collude to forge a synchronized false history stretches credulity to the breaking point. Even the astronomical records don't add up. Eclipses and comet sightings described in these texts match precise celestial calculations for those exact dates. So why does the phantom time hypothesis persist? Perhaps because it taps into a deeper discomfort with how history is written and who gets to write it. Every era has its blind spots, its lost records and unanswered questions. In the gaps between what we know and what we assume, wild ideas take root. Whether a cautionary tale about historical certainty or just an entertaining thought experiment, the theory reminds us that the past is never as solid as it seems. After all, if 300 years could vanish into thin air, what other secrets might the history books be hiding? Imagine a civilization so advanced that stars are mere candles useful for light, but too primitive to power their grandest ambitions. This is the realm of Type 3 civilizations on the Kardashev scale, beings who have harnessed the energy of entire galaxies. But what happens when even galaxies aren't enough? Enter the black hole civilization, a society that doesn't just live among these cosmic monsters, but uses them as the ultimate supercomputers and power plants. Black holes might seem like the universe's most destructive forces, but their extreme physics makes them unimaginably efficient energy sources. The key lies in the ergosphere, a region just outside the event horizon where spacetime itself is dragged into a whirlpool-like spin. Here, the Penrose process comes into play. Imagine a civilization flinging matter into the ergosphere like logs into a cosmic furnace. If the matter splits just right, one fragment gets swallowed by the black hole while the other is hurled outward with more energy than it entered with. This isn't science fiction, it's physics. The black hole's rotational energy is siphoned off, turning these gravitational beasts into galactic-scale batteries. Now scale this up. A Type 3 civilization could construct a Dyson swarm of orbiting mirrors around a black hole, directing incoming matter to maximize energy extraction. The numbers are staggering. A single supermassive black hole could provide power equivalent to trillions of stars. But here's the kicker: this process isn't perfectly efficient. Waste heat would bleed into the cosmos, and the math suggests it might look eerily similar to quasars, those ultra-bright, mysterious objects thought to be fueled by accreting black holes. Could some quasars actually be the exhaust fumes of alien megastructures? The computational potential is even wilder. Black holes are nature's fastest information processors, their event horizons acting like quantum circuits where bits are encoded in Planck-scale pixels. Theorists like Seth Lloyd calculate that a black hole the mass of our Sun could perform 10 quadrillion operations per second, enough to simulate entire universes in its lifetime. An advanced civilization might use artificial micro-black holes as quantum servers, cooling them with Hawking radiation to balance computation and energy output. The waste signatures, possibly gamma-ray bursts with unnatural regularity, or encrypted data streams hidden in the static of cosmic background radiation. Skeptics argue we'd have spotted such civilizations by now, but consider this: black hole engines would operate on timescales and wavelengths we're barely equipped to detect. Their energy signatures might blend into known astrophysical phenomena hiding in plain sight. After all, if you saw a quasar, would you first assume it's natural, or the byproduct of a civilization bending spacetime to its will? The universe is under no obligation to announce its engineers. Until we decode those cosmic whispers, the possibility remains. Some black holes might not just be objects. They might be tools. What if the Big Bang wasn't the beginning but an echo, a cosmic déjà vu reverberating across eternity, where the death of one universe becomes the birth of another in an endless cycle of collapse and rebirth? This is the spine-tingling premise of conformal cyclic cosmology, a theory that stitches time into a loop so vast it makes the 13.8 billion years we call the age of the universe seem like a single heartbeat in an infinite symphony. At the heart of this idea lies a radical reimagining of the Big Bang. Instead of a singular, inexplicable explosion from nothingness, it proposes our universe erupted from a white hole, the theoretical opposite of a black hole where matter and energy erupt rather than vanish. But here's the twist: that white hole might not be a natural anomaly. It could be the death throes of a previous universe, a collapsed cosmos rebounding like a phoenix from its own ashes. Picture a black hole so massive it consumes everything: stars, galaxies, even spacetime itself, until it reaches a point where gravity becomes repulsive, triggering a violent reversal. The singularity doesn't vanish, it reboots, spewing out a new universe in a fireball we now call the Big Bang. This isn't just poetic speculation. The math behind conformal cyclic cosmology, pioneered by physicist Roger Penrose, reveals a startling symmetry between the infinitely dense end of one universe and the infinitely hot start of another. As a dying universe expands and cools, all matter eventually decays into radiation, particles stretching into pure energy. At this point, the universe becomes smooth again. No stars, no planets, just a featureless sea of photons. Crucially, this state looks mathematically identical to the high-energy chaos of the Big Bang. Time loses meaning, scales blur. The end becomes indistinguishable from the beginning, and the cycle repeats. Evidence might already be hiding in plain sight. Penrose and his team claim to have found Hawking points in the cosmic microwave background, circular patterns of polarized light that could be the imprints of black holes from a previous eon, their evaporation scars etched onto the newborn universe like cosmic tattoos. Skeptics argue these patterns could be statistical noise, but if confirmed, they'd be the first tangible footprints of a universe that existed before our own. The implications rewrite not just cosmology, but the nature of reality itself. Cause and effect could spiral into a Möbius strip. Events in our far future might ripple backward to shape the conditions of our birth, creating a universe that's neither created nor destroyed, but eternally transformed. It's a vision where time isn't an arrow but our Ouroboros, a serpent eating its own tail across infinity. And if true, the cosmos isn't just stranger than we imagined. It's a story with no first page, no final chapter, only an endless refrain of collapse, rebirth, and resurrection written in the language of white holes and Hawking radiation. From black hole civilizations harnessing singularities as cosmic power plants to the eerie possibility that our universe is just one page in an infinite library of parallel realities, we've journeyed through theories so bold they blur the line between science and philosophy. We've wrestled with phantom stars lurking in the solar system's shadows, interrogated the holographic nature of reality itself, and even dared to ask if consciousness might be the secret ingredient holding the cosmos together. Each of these ideas, whether proven or purely speculative, chips away at the edges of what we think we know, revealing a universe far stranger, more dynamic, and more mysterious than textbooks ever suggested. So, which theory shook you to your core? The chilling elegance of vacuum decay, where reality could rewrite itself without warning. The spine-tingling whispers of the wow signal, a cosmic hello that vanished as quickly as it appeared. Or maybe it's the Boltzmann brain paradox, the existential gut punch that asks whether you might just be a fleeting quantum fluctuation hallucinating existence itself. Drop your vote in the comments below, and don't forget to subscribe for more deep dives into the phenomena bending our understanding of space, time, and everything in between. Because here's the beautiful truth: humanity's greatest superpower isn't our technology or even our intellect, it's our refusal to stop wondering. For millennia, we've stared at the stars and seen not just points of light, but puzzles begging to be solved. Every wild theory, every what-if whispered into the void is a testament to that relentless curiosity. Some ideas will fade into obscurity, while others may one day rewrite the laws of physics. But the real magic lies in the asking, the probing, the daring to imagine that the universe's greatest secrets aren't hidden in darkness, but dancing just beyond the glow of our collective understanding. After all, the next cosmic revelation might already be lurking in the data, or better yet, in the comment section below.